Hello guys, this is the last tutorial for Site 114. I'm Luke. So today we're going to talk about some numerical errors. This is also part of the final. I don't know why the projector is not working.
Oh.
Anyway, I'll just write everything down then. Like I said, today we're going to talk about numerical errors, including sensitivity and accuracy. Okay. First of all, we need there's some review about the norm of a matrix, including inf norm and one norm. Inf norm is also called row sum norm. Suppose you have a matrix like A11, A12, A21, A22. Suppose you have a matrix, 2x2 matrix. So the inf norm or row sum norm is used to, right over here, it's the maximum of the absolute value of A11 plus absolute value of A12, and here is an absolute value of A21 plus absolute value of A22. Okay? So first of all, you're going to take absolute value for each and every entry. And because it's inf norm or a row sum norm, you're going to take a sum of each row, right? If you have more entries, you're going to take a sum of all the entries on each row. And you're going to take a max operation on this array or list, right? You're going to pick the maximum. And the one norm, this is inf norm. I should put it in infinity sign over here. If it's one norm, it's I should suppose this is A. So this is A, then inf is equal to this. Okay. So and the one norm is the maximum value of going to have is A11 plus A21. The second entry is A12 plus A22. Okay, as you can see, you're taking a sum along the column direction. This plus this is this first entry, this plus this second entry. It's called column sum norm. So why are we doing this? Because it kind of tells you, it gives you a rough idea of the size of this matrix. Even though the way to compute this two norm is different, they probably have the same kind of magnitude. So either of these gives you an idea of what's the size of the matrix. Okay. So in today's tutorial, we're going to stick with the inf norm. Hope this is going to work because I'm supposed to show you some MATLAB code. Anyway, let's carry on. Okay, given the definition over here, let's do a practice. Compute a one norm and int norm of the following matrix. So the first one is a 5 minus 4 minus 1 and 7. Second one is 4 minus 1, 1, 2. Oh, very good. So a couple of minutes, we'll go through it together. The problems are shown on Okay, this is fairly simple. I'll just go ahead and solve this. So the one norm for the first matrix is we're going to take a sum of in the column direction, and we're going to take an absolute value for each and every entry. So the first entry will be absolute value of 5 plus absolute value of minus 1. The second entry is minus 4 plus 7. And we're going to take a max over this, right? So it's max of the first one is 6, the second one is 11. The max value is 11. Okay, this is the column sum norm. One norm. And the inf norm equals to maximum value take sum along the row direction, so it's 5 plus minus 4 Second entry is -1, 7. Okay, so it's max 9 and 8. So this is 9.
Literally can't do math.
Okay, as you can see, they're different, but they're at the same kind of order. Order of magnitude. Okay. So again, the metric norm is like when you have a line or segment, you kind of need to know like the length, right? Or you have 2 points. You kind of want to know the distance between the 2 points. If you distance or the length, norm, and this is like equivalent for matrix. Okay.
It's 7.
For the second one, the one norm should be max of. Now, since we have a 3 by 3 matrix, we should have 3 entries, and we're going to take a sum along the
Same thing.
column direction. So it's going to be 4 plus 1 plus 0. This is the first entry. Second entry is -1, 2. -1, 2 plus 2 plus 0. Third entry -2 plus -3 plus 4.
Yes.
And we're going to take a maximum value.
Oh yeah, I gave up.
So it's
That's
max.
just for my own notes.
So this is 5. This is 3. That is 9. So this is 9. Okay, so the one norm of this matrix is 9. Similarly, we do inf norm. I'll just directly write it down. So the inf norm for this matrix. So it's 4 plus 1 plus 2. So the first entry should be 7. Right, because we're taking some along the row direction. And the second row is 1 plus 2 plus 3. So it's 6. The third row is 0 plus 0 plus 4. Now we take a max, and that is 7. All right, again, it's different, but similar, close to each other. Okay, so same thing for the third one, because it's pretty straightforward. I'll just give you the answer. So the one norm is 7, and the inf norm is 11. For the third one. Any questions so far? Okay. All right. Once again, I will just go back to the definition part. If we have a n by n matrix A, the inf norm is defined as this, where you have you sum all the entries along the row direction. This is our row sum norm of A. And if you have one norm, you're going to do the sum along the column direction. Right? You have n entries. And then you take the max. Okay. Problem 1. Now we have some properties of norm, right? Given two matrices A and B, they're both n by n matrices. If the norm of A is greater or equal to 0, and we know that the norm of a matrix should be greater or equal to 0 because we're taking the absolute value for each and every entry, right? If you sum them together, it's going to be greater or equal to 0. Now, if we know that the norm of matrix A is 0, we know that the A matrix is a 0 matrix, which means every entry of A should be 0. Second property, if you multiply a scalar to a matrix and take the norm, is equivalent to the absolute value of that scalar and multiply that by the norm of the matrix A. And we have two inequalities where you have a sum of matrix. If you want to compute the norm of the sum, it's going to be less or equal to the norm of the sum of the individual norms. Same thing for multiplication. You have A times B, you take the norm, it's going to be less or equal to A norm times B norm. Okay? And in the next question, it's going to show in this problem 2, we're going to show why these properties are useful. Okay? This is proof problem. It's probably going to take a while, so I'll give you maybe 10 minutes and we'll go through it together.
Oh god. I'm not attempting this on my own.
Any questions? Yes?
Professor said you don't need to prove it in the exam.
Yes, I just want to show you why it's useful. Like,
He was so bad.
I think last, yeah.
I have the urge to. Okay. I'm not gonna attempt this on my own. I do not know anything about anything.
Properties.
I don't, but the other key is that we have to leave here. And I want to contact this. Oh, it's called that.
Not really. There's no way.
Everyone else is talking. Can we just go back to our notes?
That's what I meant.
Are these
Professor Berkeley said that so there's no going to be proof
except he
questions.
himself didn't know what he's doing half the time.
No matter how many times I draw this face, it always ends up looking like this.
Last term when
I can't do
did
side
this work,
profiles.
Wait, why does he have spiky hair though?
I don't know.
I can't either,
to show this process, like how we use different
What?
properties. So it's okay, it's not going to show in the exam, but it's still good that you know how to do it.
Do you just hear me? I said, do you know how to do it?
Probably will.
Boy, my time. How do you end it off?
Exactly. It looks so bad.
That looks like a monster.
It does, doesn't it?
Like a horror movie thing.
Yep.
That looks so
Yes, for
scary.
one moment.
Let's go back to art class. and
Imagine
learn how
this
to
haunting
sing.
you in your
Okay, that one's not too bad.
Are you sure?
It looks like
It could
a,
be either one.
except it doesn't look like a human.
Exactly.
It's like a
Exactly.
mouse.
It looks like one of those stone figures that you see.
The properties that I showed you in previous slides, as long as you are
Very bad.
this one, it's going to have the same kind of properties. So it doesn't matter if it's one norm or deep norm or any other kind of forms. In the group situation, we're using the property of norms. So if you're asked to impute like the actual value, then it's different. Go back first, if you're asked to impute the deep norm, you should use just ask for one norm.
Doesn't it? Isn't this the better way of spelling physics?
What?
Read this.
Physics.
It honestly should be spelled this way.
But I guess it's because it's not physics.
It's literally.
Physics. 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 It's not physics. It's physics. Okay. It's kind of like saying, it's kind of like saying that that fal and fal is the same.
Oh, true.
It's like saying. It's like saying. It's like saying. It's like saying.
Oh my god.
Abbas should be with the aleph.
Oh, I see.
You know what
Yeah.
I mean?
Small
That's
differences.
what it means. Yeah.
Small differences.
Just a little bit. So what you want to do? You want to expand the second equation here and cancel some terms using the first equation and try to make the terms on the left hand side or rearrange this what you get and put what's on the left hand side to the left, what's left on the right, and see if you can combine them somehow and combine it with something else. Yeah.
Okay, let's go.
Look at this masterpiece.
What? I think he said something. He did something like this.
Yeah, he
Wait,
kind
where
of
did
started
this-
off simple.
And then yeah.
Oh, good one, good one. Yeah, that's basically what he did.
And then I think he said something. Maybe he factored a and the x maybe.
Did he?
I don't know. I don't know. It has to do something with the. I think there's a b somewhere substituted. Oh, maybe this is gonna be b.
Oh, maybe
And
it.
then it gets cancelled out.
Sure. Sure. I'm gonna pretend I know what you just did.
No, because like I use this.
Mm-hmm.
And this is me.
Okay.
Please don't pretend you know. You can know. Nothing. Okay. And then this gets out.
Oh, true, because there is no AX there. I kind of see it.
Actually, where did the oh, there you go.
But why would you cancel it? Isn't there a B
No,
term?
because it moves to the other side. B minus B. B.
Oh, but if you cancel it though, look. Like, isn't there like an inequality here?
Oh, but there still is a B here.
Oh, there's your still.
Norm B.
Oh, okay.
However you say that.
Okay.
Okay, so now we have a okay, I think you can factor out the norm x. We can do a plus norm x. Oh, shoot, what am I doing? Okay, let's do ax plus what am I doing? I literally just rewrote what I already had. No, this is not good.
This is why I didn't attempt it.
What if we do? Wait, what do we have to get to? Oh, so we want to get this. Oh, where's x? Oh, that. So I think we have to move one of them to the other side. I think I move this to the other side because we need it. Okay. What should I move? Just give me a guess. Let's move that. Okay. So B minus X. Oh, what am I doing? AX plus.
No, the condition number tells you how a matrix is close to single. Yeah, if it's if the matrix has a larger condition number, it means it's very close to singular, or very close to invert, and not invertible, not stable. So we have condition numbers.
Is that for me?
Yes.
So heavy.
It is.
Okay, what did I write?
I don't know.
Bring it back to you. Your heart is so much better.
Thank you. very much.
How do you write straight?
How do I write straight with my wrist like
No,
that?
with like your with your tablet like that.
Good question. How do I don't know, to be honest. I think I just move my
Okay,
hand.
maybe it's my angle.
It's probably your angle, yeah.
Okay, but it's like awfully hard. Okay.
Yeah, I think you get used to
kinda
it.
hard.
Yeah. Let me actually be on task right now.
That's why there's only 6 questions.
Probably,
Okay, I kind
yeah.
of want to do this without looking at my notes. I don't know what I'm.
Oh, use the triangle inequality.
Oh, what's the triangle?
Good question. Oh, it's like this one. Something plus something. Maybe you substitute these for the norms.
What do you mean?
Good question. So whenever that's a lie. That is a lie. Can you just randomly take the norm of everything here, or do you need to?
Should I check your notes?
Should probably check some.
What note is this? Sensitivity, accuracy. Okay. So I was good up till
Has anybody finished?
here. Okay, so he moved everything except for S and X to the other side. So he even moved that to the other side.
Okay, I'll just go ahead and solve this.
Bro,
Yes.
Like I said, it's not that easy compared to the other problems, so it's okay if you maybe get stuck at some stuff. Basically, this is a problem that's showing you why those properties are useful. Probably I'll show you in the last video of this. Why these are useful and how to use this to approve some kind of thing. So maybe because it's the first year class, so you don't need to prove something. But when I took some something like machine learning class, especially if it's from the math or experiment, I got asked to prove a lot of things. And in those questions, you're using these kind of inequalities and like those properties, right? So like I said, we're gonna look at the second equation. Delta A times x plus delta x equals to b plus delta b. And the original one is ax equals b. So what does this mean? First of all, ax equals b is some system you have, right? It's system equations. And when you perturb matrix A, vector x and vector b, you're going to get a new system. If this delta A, delta x, delta b are relatively small compared to the original A, x, and b, then the new system will be close to the original system, even though they're different somehow a little bit. Okay, we're going to talk about the sensitivities that if I just perturb A and B a little bit, not a lot, am I going to get a new x that is close to the original x? If the new x we get is close to the original x, that means A matrix here is not sensitive to some perturbation, right? But if I got a totally new x, which is very different from the original x, that means A matrix is sensitive to some noise or perturbation. Okay, and this is why I'm doing this. Okay, now I'm just gonna expand the first equation over here. So it's 8x plus A delta x plus delta A x plus delta a delta x. And the right hand side is b plus delta b. Okay? Simply just expand the brackets. As you can see here, this is what we have in the second equation here, so we can just cancel them out. So what's left is a times delta x plus delta a x plus delta a delta x equals to delta b. Basically cancel out these two terms, right? And from here, when you try to prove something, you're gonna look at what you want to prove. So apparently, we want the delta x term on the left-hand side, right, and all the other things on the right-hand side. So that gives you a clue how to rearrange this equation here. So we're just gonna try to make all the terms with delta x on the left-hand side and what the terms without delta x on the other side. Okay. So from here, I'm gonna do a that's delta x. So basically, wait a second. Am I missing anything? Okay, so I'm just gonna try to leave this term on the left-hand side and the other terms on the right-hand side. So it's gonna be delta a negative actually minus delta a delta x plus delta b. Okay, so only this term on the left-hand side, the other term on the right-hand side. So now I'm gonna multiply a inverse on both sides of the equation. So it's gonna be a inverse a delta x equals to a inverse, and what's here is gonna be in this bracket. Okay. And on the right-hand side, because the A inverse times A is going to give you a identity matrix, so what's on the left-hand side is delta x, A inverse, and what's in the bracket is the same thing, so it's going to be delta A x minus delta A delta x plus delta b. Okay? From here to here, it's just some rearrangement of the original two equations. And now we're gonna take the norm of both of the equations. So the norm of delta x will equal to the norm of what's on the so we're gonna put everything here in there. Okay, and now let's try to use some properties. Well, I think I made a mistake. This should be less or equal to. We're gonna use these. I think I made a mistake. But here it shouldn't be equal. It should be less or equal to. So sorry about that.
It's okay.
Anyway, right now we have the norm. So on the right hand side is we're taking a norm of a multiplication, right? It's A inverse and some other matrix over here. So if we're looking at the properties, we can use property number 4. So we're gonna get delta x, and we take the norm here. It's gonna be less or equal to if we, separate the A inverse and the other terms. So it's gonna be A inverse times all the other terms. Okay. Now, the thing is, I have to go forward. So if you look at what we have right now and what we need to improve, one thing you notice is that right now here we have some negative values, but in the bracket we don't have that. So what we're going to do is that we're going to use the third property. Right now we have the norm of some sum. So we're going to take the sum of norms, right? And it's going to be a less or equal sign because the norm of sum is less or equal to sum of norm. So it's going to be using property number 3. So delta x is going to be less or equal to, here we're not going to change it. We're going to take a sum for each and every term here. So it's going to be negative delta ax, take norm here, plus negative delta a delta x plus norm of delta b. Okay? So we change from norm of sum to sum of norm. And this includes inequality holds. Okay, now we still have this problem where we have this negative sign. But remember, we can use property number 2, where if you have a scalar multiplied by some matrix, you can take the absolute value of that scalar and then multiply that with the norm of the matrix, which is property number 2. So from here, what we can do is, so everything will be the same, except we're going to directly take out the negative sign, because the negative sign means negative 1 multiply the matrix, right? So it's going to be, I'll just write it out. So it's minus 1 times, the absolute value minus 1 times the norm of delta ax plus, minus 1 delta x plus the norm of delta b. Okay, so basically I'll just take out the negative 1 out. Because the absolute value of negative 1 is just 1, so it just disappears. Okay? Can I erase this part? Okay. Okay, so this step we're using a property number 2. So what's left is the norm of delta x is less or equal to norm of H inverse delta ax norm of delta ax plus norm of delta x plus a norm of delta b. Okay, right now in our, we don't have the negative signs, which is exactly what we want to do. Okay, so after that, okay. Okay, so now we can expand these bracket over here. So it's going to be delta x less or equal to. So what we're gonna do? This is delta A, that's delta A. Okay, so we're gonna do this. So combine some of these two terms. So it's gonna be negative inverse times delta B plus delta A times x, and second term will be in inverse norm of delta A delta x. Okay. What property is this? It's not here, but system distributive rule. You multiply things, you can just build two different terms. Basically, we're combining this term and this term, right? And put it right. Oh, there should be a bracket. Combine these two terms and put it into this bracket. We'll have A inverse over here, and what's left is this term, and it's here. Okay, now what? Now if we look at this, what we have. Okay, so now if we look at this, what we do is that this whole term, there is no delta x in it, right? But this term, there's no delta x in it. So what we're gonna do is we're gonna move this term to the left-hand side of the equation and extract the term with delta x. So it's going to be delta x minus that term. It's going to be A inverse norm of A inverse times delta A delta x. It's going to be less or equal to A inverse times this bracket over here. Okay, so what we're trying to do is we're trying to isolate delta x. Right? Oh, before that, actually, we need one more step where. So this is less or equals to. So the first term doesn't change. Where we have A inverse. And with that bracket, it doesn't change, plus A inverse norm times delta A norm times delta X norm. What property are we using here? Number 4, right? We have a norm of multiplicity, and right now we're doing a multiplicity of norms. Questions? So from here to here, all I do is by just using property 4, I separate these two terms apart. Okay? We can think of this as A, and this is B. Right now it's norm of A times norm of B. Okay? And then we're gonna move these things to the left-hand side. So here is not the norm of the 2 anymore. It's the product of this norms from here to here. Okay?
I think you might finish early though, depending on your question too. There's oh well. That's a good point.
Now we can take every term that has delta x and take whatever left to the other side. So let me work there. Right here. So it's delta x norm times 1 minus A inverse norm times delta A norm. And it's going to be less or equal to A inverse well, inside is going to be the same, so it's delta B plus normal delta A times x. Okay, so basically extract delta x. Okay, now we're gonna divide all these things to the other side, and in order to do that, we have to make sure this thing is positive, right? Otherwise, the sign will be changed. And this is the condition. I think Professor Shute already mentioned it, where you have I don't think I have it in the slides, but I read this part. Basically, when you perturb a matrix, you don't want to perturb it too much. You have a bounds, so that after you perturb matrix A is still invertible. And the requirement there is that this part is greater than 0. So when we perturb this matrix, we kind of make this assumption already. So we know that this term is going to be positive because we don't perturb the matrix A that much. So that we can divide the whole thing into the other side. So it's going to be delta x that's or equal to divided by 1 minus delta A Okay, basically I just divide both sides by this term, and it's gonna go here, right? Now if we look at this new, it's very similar to that one, right? We have A inverse there, we don't have the norm of A. So 1 minus something here. We have delta B in there, delta A. It's different, but very close. So I would say the next step I will try is to divide both sides by norm of x. So let me see That's what it is. Yes, okay. So now we're going to divide both sides by the norm of x, because right now the only delta x term is on the left hand side already, so the only thing that is missing is the norm of x. So we're going to divide both sides by norm of x. The reason that this inequality is going to hold is because the norm of something is going to be positive or equal to 0. And here we're assuming it's not 0. So it's going to be positive, so this less or equal sign will hold. And right now, we're going to put the, you can either put the norm of x somewhere here, or we can put it into the bracket. Here I'm going to put it in the bracket, and you'll see why in a bit. So what's outside the bracket will stay the same. So it's 1 minus A inverse times delta A norm. And here it's going to be delta B divided by X norm plus this. There's a norm of X here, so it's going to cancel out. So it's going to be norm of delta A. Okay. Okay, now it looks a little more like that because this term there's no x anymore. So apparently we need a norm of a somewhere here, right? So that's the thing that's missing. So what we can do is we divide this whole thing by a norm and multiply a norm back, right? So what we're going to do is that this whole thing, questions? Delta x divided by x less or equals to. So we're going to divide norm of A inside the bracket, and we'll multiply that outside the bracket. So it's going to be norm of A inverse times norm of A. And what's left here will be the same. A inverse times delta A. And what's inside is going to be delta B divided by A norm of A times norm of plus delta A norm divided by A norm. Okay, this is a very common trick you will do when you try to prove something. You would multiply it and then divide it by something and rearrange it. Or you're gonna, sometimes you're gonna plus something and then minus something again. So it doesn't change the whole value, but it gives you the term that you needed. Okay, now if we look at
What did we divide?
okay, we have A.
We divide.
Divide by A, and also if you multiply by A over there.
Delta A. So it's slightly different over here. And what's inside here is the same. The only thing is this term is different. We want to make this term to be B, but it's not. It's A norm of A times norm of X. We know that
I don't actually
the
understand
norm
this
of
today, and I
A
didn't
times
know.
X is equal to
Oh, yeah.
I think because he struggled with us too.
right?
Do it.
But we cannot directly do that because right now it's not norm of A X, it's norm of A times norm of X. So we can use property number 4 again. Okay. So norm of A times norm of X is greater than this, right? And because it's on the denominator, and we know it's going to be greater or equal to 0, so the whole thing will be less or equal to if I change the term to this one. Did I? Oh. Okay. Let me give an example maybe. Suppose this term is 6, and this term is going to be 5, because we know this is going to be greater than that, right? Right now, if I swap this by this, there will be a smaller value over here. And since it's going to be on the denominator, this whole thing will be greater. Okay? So that means what's on the left hand side, because what's on the right hand side got greater, and what's on the left hand side doesn't change. So what's on the left hand side will be less or equal to everything here if I swap this term. Okay? So it's the inverse norm. 1 minus the inverse.
I'm trying to rewrite that.
I know. I'm just gonna copy paste it.
So it's going to be delta B, AX norm, plus delta A. Okay, now we're very close to our destination. First thing we can do is just substitute this term by norm of B, right? Because that's what we want in the we want the norm of B over here, and we can do that because it's already norm of B x not equal to B. Now the only difference, if you look at that, is this term here. We have a delta A, but as you can see, compared to what we have, you only multiply norm of A and divide by A, right? So it's basically exactly what we have over here. So we have one minus
Oh yeah, I don't know what that's wrong.
times delta B, B delta A, 1 by, okay, then it's proved. Again, it's not easy. I think the proof problems are always hard for me, at least, because it takes some inspiration. I would say some practice will definitely help, but it doesn't help all the time. But you got the idea. At least you know why it is true, and how you will need to use those properties when you see some proof questions. Okay, and another thing you might be wondering is that why are we doing this? Why we have a norm of A here and divided by norm of A? Because that is not natural. The reason is that we're going to define a value called condition number, which is this term multiplied this. Basically, the combination of these two, the product of these two is called a condition number, and it gives you some information about matrix A. And now we're going to talk about that. Okay, now we're going to talk about condition number and summative. Like I said, the condition number is defined as the norm of A and then times the norm of A inverse. And this value indicates how close a matrix is to singular. Okay. If the value k of A is high, it means matrix A is very close to singular. Singular means very close to not invertible, very close to determinant equals to 0. Or maybe there's two columns, rows that are linearly dependent. Okay. If a matrix has a higher k value, condition value, it is more sensitive to perturbation or sensitive to noise. Yes.
Can you turn your mic up because it's really loud in here? So
Oh, really loud? Sorry. What on now? Is it better? No?
yeah, it's like the volume.
Okay.
Because we can't hear you properly.
You know where it is?
I think it's just like a diagonal. So, okay, so that's fine. If you can't find it, that's okay.
I'll just put it like forward to. Who's
So, like,
sorry?
if you put it, I think you put it higher.
Oh, really? Hi.
I think he heard like it's very loud. Like I don't think he understood that she said the room is very loud. Sorry.
Oh, wow.
Yeah. No, I think like he heard that. He is very loud. He just wanted to say like she can't hear.
But if it's a volume.
Do you want me to be louder or?
No, it's just the class is loud, so it's just hard.
No.
Yeah, I can't hear you in center more than the volume. Yeah, no, I don't want
Is it better? Okay. All right, let's compute some k value. Okay, so when you compute the condition number, you're gonna compute the inverse of A, of course, because A equals norm of A times the norm of A inverse, and because you can do different norms. In this question, it asked condition number with norm inf norm over here. So you're just gonna compute A inverse first and compute the inf norm of A matrix and A inverse matrix, then multiply them together. I3 means identity matrix. That is 3 by 3. 3 by 3 identity matrix.
So just
So like,
Yeah.
so this is just.
So what do we do with the inverse?
I think there's that one formula where it's like 1 over determinant A, and then you multiply it and like you switch the diagonals or something.
And then how does the k have to do with, like, how does this have to do with what we're finding for the inverse?
So what you want to do is you want to find, okay, so K, it's like the inf norm of A times the inf norm of the inverse of A.
Okay.
So you have to calculate both of them. So the inf, whatever norm of A
Right.
is just 1 because you're adding this 1.
Right.
And I, like, it's the same as A inverse 1 because like it's the identity
Oh,
matrix.
so you're finding the inverse and you're
Yeah,
finding the
yeah,
single.
yeah. And then once you have those values, you just multiply them.
That makes sense.
Yeah.
Just so you know,
worries.
I have the solution ready for all these problems, so you can check it out after the tutorial, and it's printed. So I think it's much better, easier to understand than my handwriting.
So, infinity is a max of the sum of all of these. So like the sum of this row is the sum of this row. Is a max. Yeah. And then because it's the same row, it's one
Has anybody finished the second one?
Smartphone charger?
How much? Okay.
Oh no, I don't bring them to school.
Yeah.
Yeah, sorry.
That's 6002.
What?
For which one?
Okay, for the sake of time, I'll just go ahead and solve it. What is the condition number for question 1? It's 1, right? And like I said, the condition number tells you how far away a matrix is to singular. The higher value you get, the closer this matrix is to singular. And k equals to 1 is the lowest value you can get, which means this matrix, identity matrix, is the farthest matrix you can get to singular. That is because if you look at the columns of the identity matrix, they are orthogonal. I'm not sure if you already learned that. Orthogonal means they're kind of like vertical. if you like in 2D, they're vertical, which means they're not. That is the farthest you can get from parallel or linearly dependent. Okay. That means this is the farthest you can get from singular. Okay. And given that, without any computation, do you think the condition value for this one is going to be high or low? Just by looking at the matrix itself. It's going to be high because it is very close to linearly dependent, right? If you look at these two columns here, if you perturb this entry by 0.001, I mean minus this term by 0.001, it's going to be 1, 1, 2, 2, and then it's singular, right? It's linearly dependent, I mean these two columns. So without even computing it, you know in advance that the condition number for this matrix will be high because it's close to singular. Any questions? I hope I say that clearly because that is kind of a takeaway, like how you can remember what condition number is. Okay, let's just let's compute that value. So first of all, we need to compute the A inverse, right? So first of all, let's compute the determinant. Determinant of A is 2 times 1 minus 2 times 1.001, so it's minus 0.002. Okay, and now we can get A's inverse because it's 2 by 2. It's going to be 1 over determinant, which is minus 0.002, and swap the diagonal, so it's going to be 2, 1. And add a negative sign. This is negative 2, so this is negative 0.001. Okay? Any questions so far? All right, so let's compute the inf norm of A. So it's going to be because it's inf norm, it's going to be row sum. So this 1 plus 2 is 3. 1.001 plus 2, 3.001. And we're going to take the max, so it's going to be 3.001. Okay? Questions? Okay. Now let's check the inf norm of A inverse. Now we're looking at this matrix over here. And because this is a scalar multiplied matrix, we can use property number 2. So it's going to be, let's take the absolute value of negative 0.002 multiply the inf norm of this matrix, right? The inf norm of this matrix is absolute value 2 plus absolute value negative 2, so it's 4. And this is 1.001, 1, so the max is 4. Okay? So this is this term times 4. And that gives you some, what's the value? I think I have it. So it gives you 2,000. Okay. And now the condition number using inf norm of A is norm of A
6,000.
times norm of A inverse,
Pretty sure it's 6,000.
6,000.
and that gives you 6,002.
And then 6,000. 6,000.
Okay, compared to the first one, the condition number for the first question is 1, right? And this is 6,000 or something, it's very high. So it means it's very close to singular. It means the columns are very close to linearly
Or
dependent.
maybe you're right. Maybe it is 2,000.
I don't know. I don't
Any
know
questions?
calculations.
I can't do math.
Wait, do it mentally?
Okay.
I was trying to do
So I'm just gonna skip the next two because they're very similar. You just need to follow this procedure. Knowing how to compute
Oh, yeah.
this value is important.
times.
Another important thing is that you do have a good interpretation of what this k value means, right? I guess the easiest way to remember it is that it tells you how close the matrix is to singular. And yeah, at least for me, that's the best way to remember it. Okay. Okay, now we know about condition number. Instead we're gonna talk about numerical errors, right? And now we're gonna do something about how this condition number will tell us how sensitive a matrix is. Basically, if you have a higher k value for a matrix, that means this matrix is very close to singular, and that means it's gonna be very sensitive to noise. If you perturb A a little bit, you might get a whole new different x value because it's sensitive. Okay, and yeah, let's do this question. Problem 4. Let's 10 minutes maybe.
I have the urge to just like walk on it.
Literally. Dying.
Maybe we just walk out.
Can I just eat this one?
What?
I want to eat anything. I'm
What?
gonna eat my phone.
Eat your phone.
Yeah.
Oh gosh. Don't do that. You'll break your fast then. I mean, actually, I wonder. Will you? Yeah, maybe you will.
I mean, I'm still eating. Okay.
Yeah, actually.
I think so, yeah. If you swallow it, it's still something.
Okay. Sure.
Like if I swallow gasoline.
Infinity row or column?
1 is column. So this is row.
Infinity
Infinity's row.
row.
Yep.
So row.
But
Row.
that's a row.
I'm losing my mind. 4, 5.5. When do this to my phone?
Yes.
Yeah, I'm using my computer tonight. I'm kind of glad. Or 5 at 9.
Or at 9?
At 9.
At 9, oh yeah.
Because I feel like by the. Oh shoot, it's 5.
Yeah, I think it's okay.
Is it good?
Yeah, should be good.
What, singular?
Yeah, because if it was in the night, like if it was like evening or this time or something,
Oh yeah.
my cognitive
No,
abilities are
no,
losing
literally.
at 162.
Every minute that goes by, my brain cells die.
Literally.
Yes, it's
You know, I might
because
have some period during
not
one
invertible means determinant equals 0. Means singular. Means
Oh, actually,
the columns are linearly dependent. They're the same thing, right? So basically, if you have a very high k value, it means that, like I said,
I thought-
the determinant is very close to 0.
I don't
And
want
what
it to
that
come
means
through
is,
y'all. I wanted to skip over this one, but I'm
it's,
getting it.
Yeah, the thing is, yeah, finals are fine,
if you look at this
Are 122s
properties in the in this
Are
respective
Are 122s
implementation,
at like 6?
that means if you perturb the a a little bit
And
or
so
perturb
it's
the b value a little bit, you're
Oh,
gonna get
that's
a
right.
whole
unless she's the
new
one who told told us before.
x,
conquer
which
for
is
the
very
abilities
different
of
from
bad.
the original
Irony.
system.
Because we're fasting.
That is caused by
The performance is
the fact that matrix A is singular,
Okay.
a closed
So what's
singular.
1.5?
So if
I need to
that
actually
means
just start
the A
doing that.
matrix is not stable. Right, perturb it a little bit, we have a whole new different performance or transformation. If you have a stable matrix, you perturb it a little bit, the new system, the X you get is close to what you had before. It's nothing. Yeah, so the reason we're talking about this is that when you compute, like, do computation, like, suppose you use a computer, in DeepLab, you're not gonna have infinite RAM, so you have to truncate the number with some, digits. That means the value you have here is not the ground truth value, so there's some perturbation or some error, some noise.
Bert, imagine
And
converting
the
this.
thing we care about
No, I do
is
not have the
that
mental capacity.
can we truncate here and get a good enough approximation of x? And that depends on
Instead of
the property of A.
CFE test.
Yeah, if the p-value of A is high, if you truncate, you're gonna have a whole new different x,
Yeah.
which is
You
bad
You press on it,
approximation
it like disappears.
of the
I
ground
think
truth
they're
x.
testing something.
That's like the-
Yeah,
I think they're
but if you have
testing
a
how many
good
people are
matrix,
gonna press on it.
not singular matrix, maybe you can truncate a lot,
Or maybe
you still
with
got a
the
good approximation.
dynasty.
Yeah, that's why we care about this. Yeah.
I don't have the energy to do this for a 3-way.
No, absolutely. Is there a faster way of doing it? I wonder.
I mean, I guess the way would be to.
I mean, you do that thing.
There's 2 ways. Either you
Yeah.
can like do like reduce it,
Sorry, because
So
we
there's a
don't
bunch of
have
zeros.
enough time.
or
So
you can
I'll just
actually
go ahead and
just
solve
use
this.
these numbers.
For that, I should
Very expensive.
probably mention this before. There's a good question just now. So what singular means, or what? So when I say perturbation, why do we care about that? It's because when we do the computations using a computer, we only have limited amount of RAM. That means, suppose we have a value is like the pi, right? You cannot save this number in a computer. I mean, with the infinite digits. So you have to truncate somewhere. Suppose I use 1, 2, 3, 4, 5, 6, 7, 8 digits. That means the value you saved in your computer is not the one you actually want, which is pi, right? That means you perturb this value somehow, or there's some noise in here, right? And suppose this is just one entry in your matrix, and you're going to truncate each and every entry of this matrix, which means the A you have is not the real A you want. The thing is, doesn't matter. If it doesn't matter if the A matrix have a low condition number, because if you have a low condition number, even though you perturb A a little bit, the X you get will be very close to the original X. Okay? Because this matrix is stable, because it's far away from singular. However, if you have a bad matrix A, which is close to singular, after you truncate each and every entry, even though you only left out a little bit, or very little, because the total amount or mass after this A digits is only a little bit, because this matrix is very close to singular, you're going to get a very bad approximation of X. And that's why it matters. Okay, so yeah, basically this condition number K tells you if it matters if you truncate or if you perturb the original matrix A. Okay, let's solve this problem. Okay, first of all, let's compute the A inverse. You can get the augmented matrix and try to first have to be identity, or we can use the cofactor. So here I'm just gonna use the cofactor method. So C11 is if I cross the first column, and what's left is 1 times 0.6 minus this times this, right? So what you have is C11 is 0.0375. C12, don't forget about the sign, it's going to be 0.15. C13. C21. C22. Okay, C3 equals to negative 0.75. C31 0.5. C32 is negative. C33 is. Any question about how to compute the cofactors? No, you just you have the entry here. You just cover the corresponding row and columns and compute the determinant of what's left, right? Okay, so after we have that, we can struct the adjacency matrix. Basically, we have this. We put them into the corresponding entry 1, 1, 1, 2, 1, 3, and then we do the transpose, right? So the adjacency matrix is this: C11, C12, C13, C21, C22, C23, C31, what is it? 3, 2, 3, 2. Okay. So so what you can do is you put the corresponding entry in a matrix as you specified over here, and then you take the transpose, you will get something like this. Okay, and now we have the determinant. Did we compute the determinant? No. Okay. Determinant is that you can expand this by any row or any column. So the determinant of A equals to, let's just expand this along the first row. So it's going to be 3 times 3 because the first entry is 3, right? Now we cover up here, and what's left is the right bottom corner, and so it's going to be 3 times the determinant of what's left. So it's going to be 0.75, 0.75, 0.6. Now we move to the next entry, so it's 1.5. But because it's at the first row, second column, the sign will be negative, so it's going to be -1 plus -1 to the power of the first row, second column. So we have a negative sign over here, times 1.5, and we cross across the first row, second column. What's left is 1.5, 0.75, 1, 0.6. Now let's move to the third one. Is 1, right? So it's 1 times 1.5, 1, 0.75. Okay? Because they're 2 by 2 matrix, we know how to compute compute the determinant now. So at that we get 0.0125. All right. Now we have the determinant. We have the adjacency matrix. We can compute the A inverse.
Oh, it's okay, never mind.
What do you say?
So A inverse equals to 1 over determinant of A times the adjacency matrix of A. It gives you 3, 12, 10, 12, 4, 60, 10, 60, 60. Okay, again, you can compute the A inverse however you want. You can use the augmented matrix method. Here, use this cofactor method just as a review, so that you still remember how to do it. Okay, now we have an A inverse. We can go ahead and compute the norm of these two matrices. Can I read this part?
Remember when you taught him for Shirley?
You what, sorry?
Remember when you taught him for Shirley? On question 4?
I take back my words.
So the norm of A, in norm, will be max. We're going to sum the first row, so it's going to be 3 plus 1.5 plus 1, so it's 5.5. Second row, 3.25. Third row, 2.35. So the max is 5.5. Okay? And the inf norm of A inverse is max of, we're going to look at this matrix here, and sum of the first row, absolute value, 3 plus 12 plus 10, so is 25. Second one is 12 plus 64, so it's 76. Plus 60, so it's 136. This is 130. And the max value is 136. Therefore, we can compute the condition number of A to be norm of A times norm of A inverse. So that's 5.5 times 136, 74.8. Okay, and I just forgot to show you that okay. Suppose we have a matrix called A and the entries are 3, 1.5, 1. Oops, why it's not working? Okay. Okay, we have a matrix here. First of all, let's check the inverse. should be the inverse of A. Let's just print it out. 3, -12, 10, -12, 64, 60, 10, -60. Okay, that's good. Now we can compute. That's good. That problem here. So the norm of A should be the norm of A. And now we need to specify the kind, because we're computing the inf norm. So it's going to be inf here, and the norm of A inverse should be norm of A inverse, same thing, inf norm. Okay, so norm of A is 5.5. Yes, and norm of A inverse is 136. Okay, cool. Now we can, let's call this K1 equals to norm of A times norm A inverse. Or we can directly compute the condition number using cond A. Same thing, we need to specify the. So K1 is like exactly what we do, right? We compute the norm individually and we multiply them together. And K2 is like a built-in function of MATLAB called count. And you specify which matrix you want to compute and the kind of norm you're going to use. Okay, and okay, good. Now let's go back to this. And we have a vector B. And solve the system. You can solve the system because we already have A inverse, right? So we can multiply A inverse and there's this part. Yes, so we can solve the system by multiply B by A inverse.
Oh, isn't it like this?
And we already solved A
yeah.
inverse, so what we're gonna get is
Okay, wait.
minus 1.4, 1.6, 2.
It's really weak.
Okay, now it says let's perturb the delta B of the perturb B by this amount, which means you're going to add 0.01 to the first entry, add negative 0.01 to the second entry, etc. So what we're going to do is we're going to get a x hat. We multiply A inverse to the perturbed B, which is going to be B plus delta B. And that gave us negative 1.15, 0.24, and 3.3. Okay, if you compare this to results, it's actually pretty different, right? Especially for the second entry and third entry. Okay, and we have a quantitative measure of that difference, which is we're going to use the norm again to quantitatively measure the difference. So it's going to be the delta x, norm of delta x, divided by norm of x. And the delta x here is basically the x hat minus x, right? The difference divided by norm of x. Okay. So what's on the top is the norm of negative 0.25 1.36. Third entry. What I'm doing is this one minus this one, or the other way around. It doesn't matter because we're taking the norm, right? So it's negative 1.3. We're computing this norm, and what's left is the x norm again. And the result is, I'll just write it over here. 0.68. So it's pretty high. Because it's like a percentage. It tells you how different it is to the original one. It is different by 68%, so it's pretty high. And that is because the condition number we got is pretty high. It's like 700 something, right? Compared to 1. 1 is the smallest you can get, and 700 is pretty high. That's why when you perturb this system a little bit by 0.01 for each and every entry, you got a whole new different result over here. That's because the A matrix is close to singular. Okay. What time is it? Okay, unfortunately, I don't have time for other things, I don't think. So after that, we're going to talk about accuracy. We have another problem, 2 problems actually. What? There are 2 over here. Anyway, I'll post the solution after this. So if you have, I think it's actually better because my handwriting is not very good. If you have any question, you can always send me an email about these questions. And I think there's one thing that I'm missing.
Is this
I think Professor Burkett asked me to do format long.
Perhaps, yeah.
Actually, I don't know how to do it. Let's figure it out together. Format long. Style. Okay. Fine. Where is it? Okay.
Something was involving that food looks so good. It's big.
Okay, can I do this?
It's hard to
So right now we're representing pi using 1, 2, 3, 4, 5 digits. If I do format long, then I show pi. Yeah, we got more digits. So this is basically tells the computer what amount of bytes you want to use to save a number. So here is 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 16. So we're using 16 digits. Compared to here, we're only using 5. So this just tells us when you do different. Can you actually see it? How do I zoom in? Zoom. Okay. So this is the original one. Original number of digits of the default number of digits that MATLAB is using. That means when you do compute something with using pi, it's going to truncate the pi with 5 digits. And you know that this value is going to be different than actual pi, right? So what you get after that is an approximation using this pi maybe hat, right? It's different pi. But you can get a better accuracy by forcing the MATLAB to use format long. That means it's going to truncate here using 16 digits. Right now it's more accurate because we have more information get into consideration. Right? Yeah, this is nothing that's perfect want me to show you guys.
Thank you.
Given that we're out of time, I'll say that's it for today. Wait for time.
Thank you.
Yeah, by the way, this is how you learn in MATLAB. Whatever you don't know, you just Google it or research it. You won't be able to remember everything.
That's how I learn everything.
Yeah.
Googling everything.